absolute value to ensure that I don't end up with a negative, because I do not want the negative square root since there's a radical. And I don't actually know what x stands for, so just to be sure, I need to include that absolute value. Okay. Next, I have y to the fourth. I do the same thing. Remember, the steps are to eliminate the radical sign, divide 2n by 2, and then take the absolute value. This is when dealing with variables with even powers. Okay, so now I have y to the fourth. Eliminate the radical, divide 4 by 2, that's going to give me y squared, and then use the absolute value. For z, I have z squared. I'm going to eliminate the radical, divide 2 by 2 to get 1, and then take the absolute value of that. And I can't do anything further with this radical 6z because it's already in simplest form. Okay, there is one more thing I can do to make this even simpler, although it's not required. And recall that I said that you really only need these absolute value symbols for when you end up with a variable that's raised to an odd power. Because no matter what y is, let's say it's -2. -2 times 2 is 4. So I really don't need the absolute value around the variables that ended up being raised to even powers. Okay, this is now in simplest form, and I'm going to go through my criteria. First, I look at my radical that I have remaining, and it doesn't contain any perfect squares. So I can't go any farther with pulling out factors that are perfect squares and then taking the square root of those. So there are no perfect squares within this radical. There are no radicals in the denominator, and there are no radicals that contain fractions. So this expression meets my criteria for being in simplest form. Okay, in example 3, we just have a simple quotient, and recall the quotient rule that says the square root of a over b equals the square root of a over the square root of b. So let's rewrite this as square root of 18 divided by 5, and now I'm going to use the quotient rule to get the square root of 18 divided by the square root of 5. Okay. The problem I have now is that I have a radical in the denominator, and that is not in simplest form. Recall that if you want to eliminate a radical in the denominator, you multiply both the numerator and the denominator by the radical expression in the denominator. So since I have square root of 5 in the denominator, I'm going to multiply both the numerator and the denominator by square root of 5. And this is allowed because if you think about it, square root of 5 divided by the square root of 5 is actually just 1, and you're allowed to multiply by 1. Okay, this is going to give me the square root of 18 times 5. So now I'm using the product property. The product property that tells me that if I have the square root of ab, this is equal to the square root of a times the square root of b. So I went from right to left. These were separate. Now I'm putting them both under the same radical. And in the denominator, I have the square root of 5 squared. Okay, looking at what I have here, let's start simplifying even further. This gives me something that contains a perfect square. So 18 can be re-expressed as 9 times 2, still times 5. And recall that a radical multiplied by itself equals the radicand. So I can just change this to 5. Next step, separate out the perfect square that I had. Now, take the square root of 9, that's 3. One more step, just multiply out 2 and 5. This is now in simplest form. There are no perfect squares as part of the radicand. the denominator no longer contains a radical and there are no fractions under the radical. So the steps that I had to take were first to use the quotient rule, the quotient property, and rewrite this in this form. Once I did that, then I could eliminate the radical in the denominator by multiplying both the numerator and the denominator by the square root of 5. I then used the product property to rewrite this as the square root of 18 times 5 divided by the square root of 18 squared. Recalling that when you square a radical, when you multiply a radical by itself, then you get the radicand. So this is just 5. Also recognizing that 18 contains a perfect square of 9. So I factored that out. 9 times 2 brought down my 5. Next, splitting off this perfect square under its own radical using the product property times the factors that are left over that are not perfect squares, still divided by 5. Take the square root of 9, that's 3, times square root of 2 times 5 divided by 5. One last step to just make this 10, and that is this expression in simplest form. Okay, this time we're asked to simplify an expression that has a radical in the denominator, and that radical is a binomial. Recall that in order to eliminate this, you're going to have to multiply both the numerator and the denominator by the conjugate of this binomial. So the binomial is 3 radical 5 minus 2 radical 5. So the conjugate is 3 radical 5 plus 2 radical 3. So it's the same expression, but this time we are adding instead of subtracting. Rewriting the expression we're given. And all you have to do now is multiply both the numerator and the denominator by this conjugate. 3 radical 5 plus 2 radical 3. 3 radical 5 minus 2 radical 3. So we're multiplying the top and bottom by this expression. Well, I need to go ahead and do some multiplication and some simplification on this. First, looking at the numerator. 2 radical 3 times 3 radical 5. 2 times 3 is 6. Radical 3 times radical 5. Plus 2 times 2 is 4. Square root of 3 times the square root of 3. Now, when I look at what I have here in the bottom, in the denominator, I'm going to recognize that what I have is the difference. I'm going to end up with the difference of 2 squares. A squared minus b squared. So I can go ahead and rewrite that as follows. Minus 2 radical 3 squared oh, I actually made an error. This needs to be a positive. This needs to be a positive. Okay. Because that way, when you multiply out the first 2 terms, you'll get this. The outer term and the inner will cancel out, and then the last will also give you a square, and that's the difference of 2 squares. So this is actually the conjugate you need to multiply by, which has a positive here. Okay, so this is the difference of 2 squares. And now I'm going to go ahead and work with the numerator a little bit more. And I'm going to use the product rule. Recall that with the product rule, I can rewrite this as 6 times the radical 3 times 5. And then here, I'm going to recognize that I actually have 4 times this radical 3 squared divided by 3 radical 5 squared minus 2 radical 3 squared. Okay, The next step is 6. 3 times 5 is 15, plus 4. A radical times itself is the radicand, so that gives me 3, divided by 3 squared. 3 times 3 is 9. Radical 5 squared is going to be 5, minus 2 squared is 4. Radical 3 times itself is 3. Continuing to simplify, now we've done the hard part. This is 3 radical 15 plus 12 divided by 45 minus 12. Almost there. 6 radical 15 plus 12 divided by 45 minus 12, which gives you 33. Okay, so this took some work, but staying organized and being very careful to watch your signs when you're working with conjugates, we saw that we had a binomial in the denominator and it contained a radical. So in order to eliminate those radicals from the denominator, we multiply by the conjugate of this binomial. The conjugate is the same expression, but the sum instead of the difference. So I multiplied both the numerator and the denominator by the conjugate. Top expression gave me this. On the bottom, I have the difference of 2 squares, so I had this. Then I just used the product rule to simplify what turned out to be 6 radical 15. I also recalled that a radical times itself equals the radicand, and that allowed me to simplify all 3 of these because this became 3, this became 5, and this became 3, and then I squared the other numbers, found the products, did some arithmetic, and ended up with 6 radical 15 plus 2 divided by 33. And this is in simplest form. There are no perfect squares under the radical. There are no fractions under the radical, and there's no longer a radical in the denominator.